Good morning, friends. Let's continue our discussion about the OMS that we are applying that we are going to design based on TCP socket server based. So, in the previous video, we checked about the thread pool based OMS, in which we were maintaining two thread pools, one for connection handling, which was having a fixed thread pool of 4 threads, and the order handling pool, which was of 12 thread pools. And this connection handler pool, it was handling all the socket client requests. So there were like 4 simultaneous connections that at the same time can be handled at the same time concurrently. And after that, for the handling part, we divided that validation, enrichment, and persistent part in the thread pool, which can be done concurrently. But all these approaches that we have taken so far, for example, single-threaded OMS, thread per client request, thread per client, and thread per order parsing OMS, and the previous one, which is thread pool-based OMS. All these are very imperative style of programming. Imperative means that we are giving the instruction to the computer, and computer is performing those operations as a set of instructions and changing the state. This is also called as declarative programming or procedural programming. In the fifth approach that we are going to take, we are going to use future-based OMS, in which we are going to use the same concepts of asynchronous programming by using CompletableFuture APIs. So before we design the future-based OMS, let's understand what is synchronous and what is asynchronous programming. So synchronous, as we know that we need to wait for a task to complete to continue to work. For example, in this code snippet that I have, suppose I have got a HTTP client. Uh, Using JDK 11, we can use HTTP client in the API itself. And suppose we have got a server. This is a random server, and we want to get the data out of it. Suppose this data is a long running process. Suppose it takes around 100 milliseconds. So if we use this type of programming, this is synchronous programming. In this case, we cannot proceed further to the next line. We have to wait for the response. So if it is going to take 100 milliseconds, the CPU has nothing to do but to wait. This is also called blocking IO, in which we are blocking to get the data from the server, which may take 100 milliseconds or more time. And during that time, our CPU is idle and not doing anything. So if we try to visualize it, so our thread, which is making this server request here, client.get, so that thread is actually blocking for the operation. So our thread 2, which is our server, which is trying to get the data and give it back to the client request. During that time, our client thread is blocked. This time is a block. Only once we get the result back, only then the response is created and sent back to the actor. So this is blocking, and our thread 1 is not doing anything. During that time, the CPU is idle, or it cannot utilize anything to proceed with this thread. So as mentioned here, in other words, thread 1 can't continue with its execution until thread 2 finishes processing a task. So synchronous is very much similar to what we call as a blocking type of programming, and it will definitely slow down our application if it blocks for a very long time. And this IO, most of the blocking are done on the IO operations. For example, getting the data from a disk or from a database or from a network socket. The solution for this is that to use asynchronous programming wherever we can use it in terms of a long IO bound blocking operations. So it makes it like non-blocking, because what happens is that suppose the thread 1, it will just issue a non-blocking operation, and until the thread 2 is like fetching the response and creating the response back to the thread 1 is not blocked here. It can still continue its operation. And once the thread 2 has done it, then whatever the thread 1 has requested for it, it will create a response back and then send it. There would be a callback mechanism that thread would be notified or by some other mechanism, or it will poll it to get the data, and then it will create the response and send it back to the actor. But the point here is that right now, even though when the thread was creating the response or the reply back for the request, thread 1 is not blocked here. It can still do some other useful work, and it can wait. So there are various mechanisms that we'll discuss. It can poll on it, it can poll for the result, or it can just wait here, or it can also do other tasks and get notified by a callback method. So all these type of mechanism, but thread 1 is not going to be blocked. It can still do the other tasks if required. So and the CPU is utilized at its maximum. In Java, we have this asynchronous paradigm by using two interfaces, future and completion stage. And in the latest versions of Java, and I think in Java 7 or Java 8, we had this CompletableFuture API, which actually combines this future and completion stage interfaces, which provides us all this non-blocking asynchronous type of programming. So just for the previous example, so suppose we have got a HTTP service, and then we have got this HTTP client, which we talked about before. Now, instead of just waiting, just creating a synchronous call, client.get, what we are going to do is that we are going to wrap it into a separate thread. Here we have created a runnable task of this, in which we are fetching the data from the server. And instead of this synchronous call, we call it service.submit. In this submit method, we can we can pass a runnable and runnable or a callable message. Callable can give us some results. So here it's actually a callable because it is going to return us a string object out of it as a result, and that's why this callable is wrapped inside this thread in this lambda program in this lambda code snippet that you see. Once you call this submit, then it will immediately return this feature object, which would be having the string as the return of this. And now this main thread, which is calling all this submit method and all, this thread is not blocked. It can still do some other stuff. And then finally, after some time, it can call this feature.get, which is actually a blocking call. And by this time, after doing this stuff, and there is some time gap there, right? So suppose it takes around 100 milliseconds, and after 100 milliseconds, we again call this get, which is a blocking call. There are various ways we can avoid this blocking. We can have a overloaded method where it can just wait for a certain period of time. We'll go into all this type of details. But the idea is that this thread is not blocked, and after some time, if we call this get method, it will get the response which we expect from this client.get call. This is the beauty of this API, that we can just use a feature for all this asynchronous programming, and our main thread is not blocked. Now let's use all this concept that we have learned about completion stage and this future interface. So we have got this CompletableFuture class, and now our order handling logic that we designed before in our thread pools. Now in the future-based OMS, we can replace that logic for validation, enrichment, and persistence into CompletableFuture supply async. So this is supply async is a way mechanism by which we can supply async is something that it can wrap a callable instance. So because we are expecting an order object back of it by using this, so that's why it's callable, and that's why we are using a supply here, supply async. If it's runnable, which does not return anything, it's like sort of like runnable instance. In that case, we can use run async. Run async will not return any object. But here, because we are using a supplier, which we expect a value back, which is same as callable, it means that we have to use supply async. But the idea is that this is all done asynchronously. For example, the order validation, enrichment, and persistence. So these three, once they are done, and then we get the supply async, which means that we get the order object back. After that, we can use this type of paradigm where we are just creating the new order request, and then we are doing all this validation, enrichment, and persistence by calling join on each of it. By join means that it will wait until we get the value back, unless the validation is done, enrichment is done, and persistence is done. So as we have mimicked it, that it will take, each of these operations will take 1 second each. So all this can be done concurrently. And I hope that by this time, because these are like very simple like APIs, we are not actually doing any validation on the enrichment logic, but it's more about it's just delaying there. So what will happen is that all these three would be still done in parallel, and that's why the performance of this is going to be improved further in terms of latency. We'll see that. So if we look at our previous example of a thread pool based OMS, we have seen that we are using a executed fixed thread pool of 12 threads. And then we are performing this by using execute, and then we are using a countdown latch to integrate this. In the future based OMS, everything else would be same. For example, let's quickly go through it. So it's again same as thread pool based OMS, where we will be having a connection handle pool of 4 threads and order handle pool of 12 threads. And once we have got this client request coming, and when we are handling it, we know that this will take 1 second, right? After that, we have just change the logic here that we are using supply async method. As we discussed just now, that just before that, we are because this is a callable, we expect an object back. That's why we're using supply async instead of run async. And we are actually passing this order handler pool, which means that instead of using the default thread pool, which is created when we actually start our application, we are delegating all our requests to this executor pool, which is of consisting of 12 threads. If I don't use this, then CompletableFuture can still run, and it will use the default thread pool, which is created when we are, which is based on the number of parallel virtual code threads that we have in our system. The most important improvement here is that we will see that right now we are using this order handler pool, right, to handle all this. So we, for example, all this handling is done inside this order handler pool, and this so whenever we create this request object from the socket, right, this is going to take 1 second, right, and all this validation, enrichment, persistence, that is also done by the same thread, which is order handler pool. So it means that these three operations, along with the creation of the new order object, this all can run concurrently. So this take 1 second. The creation of this new order request, validation, enrichment, and persistence. All these four operations can be done parallelly, because as we have seen that this only takes the request. It doesn't need even the order object itself. This is where we can improve it by further 1 second, the latency of it. So once we have these four operations, like creation of the new order also, because this new order is not required for here, we are just using the request object instead of the order object. That's why all these four operations can run in parallel, which means that it will take 1 second, 1 second again. So it would be all this one is done, and then finally 1 second for sending to downstream. So from the previous example, in which we were using the thread pool OMS, it was going to take 1 second each because it was actually validating on the order. So we needed the order object for validation, enrichment, and persistence. That's why it was taking 1 and plus 1 for 1 second for this, 1 second for creating the new order object. That is 2 seconds. Then this all three can be done in parallel, so 3 seconds. And finally, the fourth second was to send it to downstream. But here we have got improvement of 1 second, because we don't need the order object anymore because of this paradigm that we are using CompletableFuture. It only needs request object, and that's why all these four options can be done in 1 second. So 1 plus 1 plus finally 1, it is going to take 3 seconds. And this we will notice once we actually run this program. So let's run our program and see. So I've got this feature based OMS, and we claim that theoretically that it's going to reduce the latency from 4 seconds to 3 seconds. So let's watch this. So now I have got this listening on this port 8080, and then let me run for say 4 clients simultaneously. If I just run this socket client 4, so it's going to make simultaneous phone connections, and let's see. Okay. So as you can see that order sent to downstream around 3 seconds, 3 seconds, 3 seconds each. So now it is a tremendous improvement from the previous examples, from 4 seconds to 3 seconds. Let's do a quick recap. So in the previous examples where we actually needed the order object, that's why it was introducing 1 extra second. But using this CompletableFuture supply async paradigm, we were only relying on this request object, which was created first by the socket, not relying on the order object. That's why all these 4 operations were done in parallel. And that's why it reduced from 4 seconds to 1 second. So 1 second for here, 1 second for this, because this is all done concurrently, and then sent to downstream 3 seconds. And this we already noticed in when we run our demo program. Now let's talk about the caveats here. Here we are using join. As we know that if you've done the previous lot of concurrency programming, we see that join is considered one of the blocking operations. And if this latency can take a lot of time, and every time we are waiting here, and this may affect the other, because what will happen is that it will take the maximum time for each of these requests. For if we are running this 4 operations in parallel, it is going to take the maximum time of it, whichever is taking the maximum time. For example, here we have mimicked it to use 1 second each. But for example, if this operation takes say 2 or 3 seconds, other taking 1 second each, but this is taking 2 or 3 seconds. So this operation all will take 3 seconds max. So it will add to the latency, because right now we have mimicked it to take 1 second. That's why this can be a problem when we are actually writing a real OMS. So and also this join actually blocks for each of these requests, which is not good. So we have reduced the latency from 4 seconds to 3 seconds by using this CompletableFuture API. But still, we are using this join method, which is blocking, and this can create two type of problems. One is the deadlock problem. Although we are trying to avoid this by creating two separate thread pools, right? So we are creating order handler pool, and we are creating this connection handler pool. So there are two separate threads. We have avoided this deadlock problem. But in the real scenarios, when we are writing a real world OMS systems, in that case, there might be many more thread pools, and that's why it will make the code quite complex if you are using a lot of blocking cost, join method, and all, and it can also introduce deadlocks. And the second problem is blocking and unblocking threads, even in the best of scenarios, has a non has got some cost. The actual parking and unparking of threads by the OS takes time, because the cache which is maintained by the processes by the CPU, that would be overwritten by other threads whenever we have a context switch. So keeping in mind these two type of caveats by which is introduced by the join method, in the next approach we'll see how we can improve the design by using futures with callback OMS. So instead of using supply async, we'll explore some other APIs and try to use features with callback method to improve this design and avoid the caveats that we have found using join method and the blocking method, you can say. So see you all in the next video.